Okay, it's a great pleasure to introduce Tommaso Pacini from Torino that will speak about Ricci curvature, convexity of volume, and minimal Lagrangian submanifold. Thank you, Tommaso.
All right, well, thank you, Emilio. Thank you to the other organizers, and thanks to all of you for being here. Let's see, my idea is to turn off my video because my internet connection is never great. And I'd also like to encourage all of you to interrupt me whenever you feel like it. So I feel like the title of the course, sorry, the course, no, it's short, don't worry. The title of the seminar is already pretty much says it all, so I don't need to start off with an outline of what I'll be talking about. It will be about relationships between Ricci curvature volume and applications to minimal Lagrangian submanifolds. But I guess we can pass on, let's see, I can make this bigger. We can pass on directly to the first slide. So I'm going to give a lot of room to explaining a bit of context, which hopefully is somehow useful. Okay, so the first bit is about Riemannian geometry. So of course, you all know that there's a lot of curvature tensors. The full curvature is of type 4-0. We can trace it once and get rid of two of those entries, and we get something that is a tensor of type 2-0, so something of the same type as the metric. And in fact, later on, we will be using the Einstein condition, which precisely says that Ricci and the metric are supposed to be pretty much the same thing. But going on, then there's the weakest form of curvature, which is scalar curvature, in which tracing again, we get rid of all tensorial input, and so we just end up with a function. So of course, one of the big questions in Riemannian geometry is to trace which aspects of the geometry depend or are influenced or controlled by each of these forms of curvature. And so, well, let's see. The starting point here is the fact that if we look at a point in the ambient manifold, and we introduce normal coordinates, then the metric itself can be developed using a Taylor expansion. And of course, you start off with 0 or 1, so delta ij at the initial point. And then because these are normal coordinates, there's no first order term. And so you skip directly to the second order term, and that's where the full Riemann curvature appears. Notice the sign. Now, our interest in this is that if you then trace these relationships, what you actually get is an expansion of something else, and that is the volume density function. So if I think of the volume as being a top form, then of course it's a multiple of dx1 dxn, and the square root of the determinant is precisely that multiple. And again, that can be expanded. It's a function, and it starts off at 1 because infinitesimally we've got the standard metric. And then once again we get minus, we get no first derivatives, and we get minus Ricci. And the fact that there's a minus there means, for example, that positive Ricci means that you're actually packing less stuff than you would have expected to. Now, this is a local computation that, of course, depends on a Taylor expansion, so it doesn't move out very far. But it turns out that the same conclusion can be reached by other means. In particular, the Bishop-Gromov theorem tells us that that same conclusion holds even for big balls. For any ball in the manifold measured with respect to the Riemannian distance, you can compare balls in your manifold with standard balls depending on the Ricci curvature. And so this is supposed to convince us that the Ricci curvature does control, or is related at least, to volume. That's the relationship we want to develop. Now, volume is, of course, an important ingredient in submanifold geometry, simply because given a submanifold, you can produce a volume form, integrate that, and you get the volume of the submanifold. Now, what you create this way is a functional on the space of all submanifolds, which is a huge infinite dimensional space. So the question is whether Ricci also encodes something about this particular manifestation of volume. And well, yes, it turns out there are some perhaps somewhat sporadic examples of this. In particular, there's a theorem by O from the early 90s, I think, which, as you see, says, well, let M be a Kaehler manifold and restrict the volume functional to only look at the Lagrangian submanifolds. We'll be discussing them further ahead. At the moment, I'm just interested in giving you a taste of this relationship. And it turns out that when the Ricci is non-positive, then the functional is convex, but only in a very, very restricted sense. It's convex only in certain points, at special points, and these are minimal Lagrangian submanifolds. What convex means here is simply that the second variation is non-negative. So the second derivatives are larger or equal to 0, as in any finite dimensional situation. But you see this, I really want to underline the fact that this calculation only holds at minimal submanifolds. The minimal submanifolds are critical points. And the notion itself of convexity is very much simplified at critical points. So that's why this notion of convexity just boils down to these two derivatives computed in the simplest of ways. But anyways, what we're getting is that negative Ricci implies convexity. Okay. Okay, if there's no comments from any of you, I can move on to the second part of this context, because this is a talk about, I mean, these are, what is it, geometry with symmetries. So I should talk about symmetries. And again, I want to emphasize a certain hierarchy. Symmetries can be extremely strong. So that's when you talk about homogeneous or symmetric spaces, and there the action is transitive. Or symmetries can be rather weak. So for example, this could be the situation where you have a fibration, and the action is transitive only on the fibers. So I call these homogeneous fiber bundles. And then, sort of like in the story of Goldilocks, there's the intermediate situation. And let's see, I'm just going to give you an example. Toric manifolds. I shall avoid the proper definition. I just want to emphasize a point of view which will be useful to us. So we're going to go back to fibrations. So M fibers over B, and we're going to assume again that the fibers are the orbits of a group action, which is a torus, hence the name toric manifolds. M here is complex, and the extra feature compared to the previous situation is that actually the torus, this Tn, action can be extended to a much larger action. It's known as the complexification, the complex torus. It's the C star to the n, which complexifies U1 to the n. Now, we're not back in the initial situation because this larger group action is not supposed to be transitive. However, it is assumed to be almost transitive, which means that the full manifold is a union of one very large orbit, which is open dense, and it corresponds precisely to the C star to the n because the action there is free. And then we assume that the remaining points inside M, which are not part of this big orbit, are however organized into a finite number of smaller orbits. These are lower dimensional objects. And so from this point of view, we see that M is really just the compactification of one initial big orbit, which is C star to the n. So, of course, there's a huge theory about toric manifolds in various contexts. Lots of it boils down to generating a picture, I'll call it the standard picture, in which we can assume that the base space is a convex polygon. And so I want to emphasize how this picture is related to the group actions. So the convex polygon is a compact closed object. Its interior is the base of that large orbit I was talking about. So each point in the interior of B parameterizes one of those initial torus fibers. When you move to the boundary is when you find this collapsing phenomena, or the compactification phenomenon. And so each facet of the boundary will be the base of one of the smaller C star to the n orbits, and points there will be lower dimensional tori. Okay, so a very stupid remark is that this is a big subject, and well, it's stupid up to a certain point, because sort of what I'm trying to get to is that I'm vaguely surprised that that I'll be able to tell you something which I think is new about this subject today. Okay, so we want to generalize this example of toric manifolds, and one can do it in the following way. So because C star to the n is related to the initial torus in a very specific way, well, that can be generalized. You can take any real compact Lie group and build something known as its complexification, which is a non-compact complex Lie group. And from out of this, you can build some geometry known as a group compactification. So by this, I will mean a compact complex M with an action of this complexified Lie group, which once again, as before, contains only one large, dense, free, open orbit, which is isomorphic to the complexified group. And once again, I'll assume that it becomes compact by adding in a finite number of lower dimensional orbits. And so, once again, if I look at the restricted action, the smaller action of the initial Lie group, well, what I'm finding is a fibration of the manifold over some base space. Okay, so this topic also has been developed quite a bit for quite a long time. well, particularly interesting recent development here has been some papers by Wang, Zhu, and Delcroix, who study stability and existence of invariant Kähler-Einstein metrics in these more symmetric cases. Of course, by now there's a general theory about this, but it was interesting, it still is interesting to see how that general theory simplifies or adapts to the presence of these large symmetry groups. Okay, so I think that's the end of the introduction. And so what I would like to do is come back to this relationship between Ricci curvature and volume and see, again, how it adapts to the presence of symmetries. So my context will be a Kaehler manifold, which I assume to be the group compactification of some Lie group. And the volume functional, which I will be looking at, similar to O's case, will be a space of submanifolds, and these will be the orbits of the smaller group. And so this is going to be simply a finite dimensional space parameterized by the base of that fibration. So I've simplified O's situation quite a bit. On the other hand, yes.
And this base vita has the dimension of the real group G. It has the same dimension.
The base, yes, the base will have.
Okay, thank you.
Yes, M will have dimension 2n. The base will have dimension n. G will have dimension n.
N. Okay, thank you.
Thank you. Thanks for interrupting me, and please, everybody else, do the same. But I was saying, compared to O, instead, I want to make something a little bit more. I mean, I want to enrich the picture here by not just looking at special orbits, special submanifolds, but I want to try to find convexity, concavity results that hold throughout the whole base space for all submanifolds. And as I was saying, the problem there is that this requires, first of all, defining a notion of convexity, which in turn requires a connection. And so I'm going to have to find a connection on my base space, use it to define the second derivatives that will produce my convexity, concavity, whatever. Okay, so this is the basic version of the main theorem that I'll be talking about. I'll give you several flavors of this theorem. M will start off in that simpler case of toric manifolds, assuming that there is a Kaehler metric, as in O's case, and that this is invariant under the smaller group action. And I want it also to be Hamiltonian in the sense of symplectic geometry. And then, as I was saying, I'll look at the volume functional on the set of the Tn orbits that have not collapsed. So on that, the B circle on the interior of B. Then the result is that, that there is a perfect matching between the sign of Ricci curvature and the convexity of this functional. Perfect in the sense that I write here, it's an if and only if in both cases. So Ricci is non-positive, if and only if something is convex. It's non-negative, if and only if it's concave, so minus that same thing as convex. And what you see is we're actually talking about the logarithm of the volume, which is actually nice because it gives a bit more information than the volume itself. If the logarithm of the volume, if the logarithm of a function is convex, then the function itself is convex. So it's a stronger form of convexity. But as I say, I was sort of surprised to see that there was such a strong relationship between curvature and the properties of this functional. So I'm going to give you the proof, and I mean, thinking back, it's something I almost never do in a seminar. But I think in this case, I will try to prove the result, because the proof is really very conceptual and it explains a lot, I think. So I need a little bit of just a first input from Kaehler geometry, and then I just need to stare at the problem and see how it works out. So the initial input is a standard formula for Ricci curvature, or for, let's say, for a variation of the Ricci curvature called the Ricci 2 form, which has just been twisted by J so that instead of being symmetric, it's anti-symmetric. It's exactly equivalent. But what one finds is that formula, it's minus I dd bar of log of the length squared of a section, of a holomorphic section of the anti-canonical bundle of the manifold. Okay, this formula is computing, what it's really doing is it's exhibiting the Ricci curvature as the curvature of a certain connection, the canonical connection on this line bundle. But what's interesting is that we can develop the length of sigma a little bit. If you think of sigma as, well, it's a form, so it's a wedge product of simpler vectors, v1 through vn. All of these will be holomorphic, and then the length is simply computable by the standard determinant formula. And if you look at it that way, well, then it looks like volume form, and all we have to do is figure out what it is the volume form of. And so to do that, as I say, I will, so let me choose these vectors, these initial vector fields carefully. They will be the fundamental vector fields of the action, the group action. And so by definition, they're tangent to the orbits that I'm interested in studying. Now, the action in this context is holomorphic, which means that the vector fields themselves are holomorphic, and that's what's required by to use the previous formula. The fact that the action is assumed to be Hamiltonian means that these orbits are Lagrangian. So now I'll define this condition. It just means that the Kaehler form, the Kaehler 2 form, the symplectic form, is 0 along the orbits. And that's one of the ingredients of the Hermitian metric. H is G plus I omega. And so it vanishes. And what I find is that the bit that I'm interested, the determinant of H, is actually the same thing as the determinant of G in this case, which is the square of the volume density of the orbit. Now, as a last observation, the action is also isometric. And so this quantity which I'm looking at, the volume density, is actually constant along the orbits. If I move up and down along orbits, I'm not seeing any change. So that means that the volume of each orbit, which is supposed to be the integral of this function, is actually up to a constant, is just the value of that constant function. Okay, and of course it becomes 0 on the lower dimensional orbits. So the summary you see is that Ricci curvature is basically I dd bar of the logarithm of volume, and this is the volume of the orbits. So this is a general fact about these Kaehler toric manifolds. Okay, so I want to move towards talking about the convexity of this volume functional. So I need to relate the operator I d d bar, which appears in Ricci, to the Hessian on the base. And so the big step here is to completely forget about all that vast literature that I was mentioning about toric manifolds, which sort of, if you've read it a few times, will automatically push you in a direction which today is not useful. Instead, what we will do is, so instead of talking about that base as being a convex polytope, what I'll do is I'll just look at it as the result of taking the complexified Lie group and quotienting it by G, so as to get the orbit space from the standard point of view of Lie groups. And by doing this, magically, what appears, and which we would not have noticed otherwise, is the fact that the base space has a natural connection with which we can define convexity. This connection is a purely Lie geometric object. So if I do this, for example, in the toric case, well, then it turns out that it's also useful to change coordinates so that my quotient space, let's see, my complexified group using the logarithm or exponential map just becomes a quotient of standard complex space in which I quotient in the vertical directions by 2 pi I. And when I take that and I quotient again by this 2 pi I, the only thing that I've left is the horizontal x variables. So that's just going to be a standard Rn. And my notion of convexity just becomes the standard convexity. Okay, but the point is that that standard convexity does remember that this is coming from Lie groups. And so now there's just a very simple fact. Let's look at our complexified group over this new base space. And first of all, let's look at functions which are invariant along orbits. That's what this F is the pullback of a capital F means. So that's the situation that we're most interested in at the moment. Well, it turns out that being plurisubharmonic above in the terms of complex geometry is exactly the same thing as being convex in the standard way below on Rn. And one can jazz this up a little bit by also looking at functions which are not invariant. We will need this later on. In that case, if you want to compute the volume, well, you really at this point do have to integrate along the vertical y directions. And then you lose the if and only if. You only get one direction. Plurisubharmonic implies convex, but not vice versa. Of course, because the integral is losing information. Okay. There's a very quick proof of this simply by writing out all the derivatives that are involved in these operators, I, d, d bar, in terms of second derivatives in x and y directions. And the point is, if you then, well, if it's invariant, then the y derivatives disappear automatically. And so the function, the I, d, d bar will be positive if and only if the Hessian is positive, because that's the only thing that's left. And if you integrate instead, well, all those y derivatives will disappear under integration by part, under integration by parts, yes, and so you get the same result. So it's a very simple fact there. Okay, so that proves. Sorry, that's the end of the proof, because what I've said is. Once again, I take Ricci, I notice through a classical formula that it can be seen as I d d bar of a volume functional, of the volume functional that I'm interested in. And then I see that through these abstract function theoretic arguments, I dd bar is going to have the same positivity as the Hessian of that volume functional. So that's it. Let me explain why this type of result is interesting. It gives a very simple proof of a nice result by Gonzalo Rivera and Rosa Senadias from a recent result from last year, which says the following, that when you're looking at toric Kaehler manifolds with positive curvature, then the volume functional has a unique critical point, which corresponds to the maximum point of that functional, and it is minimal Lagrangian. So let's see, some of this is obvious. The fact that there is a critical point in this finite dimensional space of orbits is clear from compactness. The fact that it's minimal Lagrangian is again obvious because in this context everything is Lagrangian and the critical point is minimal. The fact that it's a maximum, well, that's the critical point that we're looking at. But the fact that it's unique, that required a bit more of an argument in their case. But you see, it's obvious if you look at it, knowing that the volume is strictly concave. In this case, what we get is concavity. Okay, and I just wanted to point out we only look at the positive Ricci case. So we have results on both positive Ricci and negative Ricci, but in the compact case, it's only the positive Ricci which is relevant, because the negative ones don't have enough symmetries. Okay, so now I'm going to move on to a revised version of the same theorem. In the more general case of group compactifications, the big difference being that now the group itself is not abelian. So again, M will be compact. It will be a group compactification with an invariant Kaehler structure. I'm going to look at a volume functional, but you notice I wrote it in pink because it's a slightly different volume functional than before. And the other bit that's pink is the fact that the if and only if has disappeared. It's almost the same result, but only in one direction. If Ricci is small or equal than 0, then I get convexity, the strong convexity for the logarithm of the vol j function, and so forth. Okay. In this context, it's perfectly reasonable to look at the G invariant metrics, but later on we will weaken also that assumption. So I'm going to go through very quickly the proof of this too, because it brings in a new ingredient, which starts with the fact that the orbits are suddenly not Lagrangian anymore. To explain this, let me say that that initial definition that I gave you of Lagrangian can be rephrased. What it says is that if I take the tangent space of the submanifold and I hit it with J, I move it completely away from itself so as to get the normal space. And the two of them dimensionally sum up to give me the ambient. So that's the Lagrangian condition. And of course, there's an obvious way to weaken this by just saying that the two spaces have 0 intersection, but they're not necessarily orthogonal anymore. Okay, so that's as I say, it's a classical condition in the literature in complex analysis for people looking at approximation theorems for holomorphic functions. It turned out that the geometry of these submanifolds had not really been looked at very much. Jason, who's here with us today, and I thought about this for a few papers. And what we noticed basically sums up to saying that you get a lot of the same results in this weaker setting if you use the appropriate volume functional, which is a perturbation of the previous one. So what is this volume functional? Well, let me first remind you what the standard volume functional is. You take tangent vectors, you wedge them to get a top form, and then you normalize them with G. So that's the volume element, and of course you integrate it to get the volume functional. But if you're starting with a totally real submanifold, then it makes sense to normalize the same object in a slightly different way using the Hermitian metric instead of using the Riemannian metric. And the reason that makes sense is that top volume form, which was initially just a real form, can actually be complexified in a completely canonical way, and it becomes an element of the canonical bundle. Let's see, yes, the canonical bundle. So, the good news is that there's absolutely no difference between these functionals if you're working in the standard case of Lagrangian submanifolds, which is why nobody ever bothered to look at alternative functionals. But if you start looking at totally real submanifolds, then it turns out to be a good thing to do. And in particular, the reason for that we see now is because, let me just give you this alternative expression for the volume element. Instead of dividing by the normalization, I can multiply by the square root of the determinant of H. And of course, that's the same thing that we've been looking at before when we were looking at the formula for Ricci. It's that same determinant of H. Okay, so this suggests that we can use exactly the same proof using exactly as before the fundamental vector fields of the G action. Once again, you have all invariants so that the volume is actually, it's supposed to be the integral of this volume element, but it's just the volume element itself because that is invariant. Where the previous proof breaks down is in the function, the function theoretic support. But it turns out that there already was a theorem in the literature going back to the 80s, which does exactly what we need. So it says, well, in this same context of complexified Lie groups, you can compare, well, first of all, you could look at the functions that are invariant under the smaller group, and then you see you only get a one-sided result if the function on the big thing is plurisubharmonic. Then the function on the base space below will be convex with respect to that notion of convexity that I introduced before. And more generally, you can integrate this and so forth. Okay, so it's pretty much the same thing, but it's slightly weaker because we're not in the abelian context. And well, that gives us everything we need to prove version 2 of that theorem. Okay, so at this point, I think it would be very appropriate for one of you to make a nasty remark, which is to say, well, this is all just very tautological. We've basically, it looks like we've defined the J volume precisely to make this work. And in some case, in some case it is true, except that we started working on the J volume many years before. I noticed this, this relationship here. But I think the point is the J volume actually encodes a lot more. And it really does encode all the special features of totally real submanifolds. So first of all, it encodes a topological fact. The fact that you can define it, even just defining this J functional, shows that the canonical bundle has a special, of the ambient, has a special property compared to totally real submanifolds, which is that it trivializes. And now what we're seeing is that there's also a nice geometric interplay between ambient geometry and ambient geometry, I mean specifically geometry of the anti-canonical bundle or canonical bundle, and the totally real geometry of the submanifolds, okay? I think that's why this J volume is interesting. And also, I wanted to point out, as you see here, that the theorem I'm proving really, in the end, boils down to exactly that function theoretic statement. The two are almost equivalent, one to the other. So I find that the theorem is a nice visualization of a completely functional theoretic statement otherwise. Now we're going to come back to more surprises in this J function, J volume. But before doing that, let me give you the final version of that same theorem, in which, once again, I'm working with group compactifications. And this time I'm removing the need for invariant Kaehler structures. It's a random Kaehler structure. Again, I'm going to be looking at the J volume on the same set of G orbits. And you see only half of the previous theorem survives for all the same reasons. But the point is, that it's slightly harder to integrate in this case. In this case, the volume really is the integral of a logarithm, and I need to play with it a little bit more to get the logarithm of the integral, which is the logarithm of the volume. So there's slight changes, but again, it's based on Lassalle's results. But you see, as I try to weaken my assumptions further and further, I lose more and more. And so, yeah, there's no version 4 of the theorem. Instead, what I'm going to give you is an application, a second application along the same lines as before. This is about minimal Lagrangian submanifolds. I mean, I could already state something about existence of J minimal orbits, but I don't think you would be interested in that. So instead, I'll do something, I'll go back to the more standard situation of minimal Lagrangian orbits. And well, we can use our results also in this classical situation, as you see here. So let's see, M is going to be a positive Kaehler-Einstein manifold. I'm only going to assume the G acts along the fibers. So I'm in that weaker situation of symmetries that I was talking about at the beginning of the talk. And so the point is that any positive Kaehler-Einstein manifold with enough symmetries will automatically contain, this is my claim, a minimal Lagrangian submanifold. I cannot claim that this minimal Lagrangian is unique because my previous theorems are not strong enough to give me a global concavity as before, but I can complain that, not complain, sorry. I can state, whatever, that the orbit is isolated. So I think this is also a new result, existence of minimal Lagrangian submanifolds in the setting. But let's see how we get this. So once again, we're in a compact situation, so it's clear that we will have a critical point, at least for the J volume. Yes.
Can I ask? Sorry, can I ask you again? So in the previous theory,
Yes.
this isometric action doesn't imply also transitivity, not necessarily, right?
Sorry, say that again.
In the previous page, in the slides, in the previous theorem, so now in this theorem, this you have this group acting isometrically. This doesn't imply also transitivity.
Not transitively, no. I'm not assuming that it is transitive.
Yeah,
I'm
asking if the action acting isometrically implies that it is also transitive. I have this feeling.
Transitive? No, it will.
I mean, isometric action is very strong condition.
Well, yes. I mean, it is a strong condition because in Kaehler-Einstein manifolds, this is something that I will need. If it's an action by isometries, it is automatically and also an action by automorphisms. But the space of automorphisms is twice as big as the space of isometries. The isometries are the Lie group, the Lie algebra, sorry, of isometries is again, it's totally real inside the space, the Lie algebra of complex automorphisms. So, sorry, I went in the wrong direction. This is the slide. I'm not sure if I answered your question.
Okay, thank you.
Okay. Anyways, the point is, the previous analysis about J volume and so forth will only initially produce for us a critical J, a maximal, let's say, J volume orbit. So something that is computed with respect to the wrong volume function. But then it turns out that there was that we can use one of the results that Jason and I proved I don't know, a couple years ago, which says that in this Fano case, being J minimal is equivalent to being minimal Lagrangian. And so even though the generic orbit is only totally real, this critical orbit will be Lagrangian. And so then we fall back onto the standard volume functional, and the statement is can be made about the standard minimal Lagrangian orbits that people are interested in. So that's the proof of this this corollary. I just have two more things to say. One is to try to emphasize once again what is the role of totally real geometry in this context. Well, what I just claimed is that totally real geometry is sometimes a useful intermediate step in proving something about Lagrangian submanifolds, which basically means that complex analysis can be useful in saying something about Riemannian symplectic problems. Of course, this is due to the Kaehler context, but this is a new manifestation of this principle. These same methods were used by us already, again, for other purposes, concerning the persistence of minimal Lagrangian submanifolds under perturbation. I also wanted to point out that that some of this is interesting from a different point of view, which is the possibility of doing submanifold flows which are analogous to Lagrangian mean curvature flow. But then the other thing that I wanted to say is there's a second very important input that's coming into the game here, which is the role of function theory. As I was saying, basically what we're doing is taking function theoretic statements and translating them into geometry. I feel like this is something that can be developed further. And indeed, I started speaking with, talking to Annafino in Torino about this sort of thing. And we're trying to push both the function theoretic framework and the geometric consequences into new directions. But anyways, I think I can stop here. So thanks to all of you. And I'd welcome any questions or any references to literature that I don't know about.
Okay, thank you very much, Tommaso. Very nice talk. Are there other questions for Tommaso? Question or comments?
I have a question. Can you hear me?
Yes, yes, go on.
Okay, so Andreas Bernig from University of Frankfurt. So I have a question on the J volume. If you take some submanifold inside the Kaehler manifold, you can associate to each point some so-called Kaehler angles, multiple Kaehler angles. So for instance, if the submanifold is Lagrangian, then the Kaehler angles are all pi/2, and if it's totally real, then the Kaehler angles are all non-zero. And so is it possible to describe the J volume as some integral of some function depending on the Kaehler angles?
I think the answer is yes. I think at some point we looked at that, but the formula was not particularly appealing. Of course, the totally real condition poses almost no condition on those angles, except that they are non-trivial. It is an open condition, and so the angles can change quite a bit. But yeah, I think you can encode the. You can rewrite the J volume form first of all in terms, so the HVI/VJ encodes those angles, and then you just, as you say, you're just integrating those.
Mm-hmm. Okay, thank you.
Other questions? Any other question? Okay, if not, we thank again Tommaso.
All right, well, thanks again to all of you, and I hope to see you in person sometime soon.
I hope so. Let me stop the recording.